Oh man, I am so psyched for this video. We're talking about how to find critical numbers, what they are, how to find them algebraically. Let's do this. So critical numbers, little formal definition here. On a graph of some function f of x, if f prime of some number, so the derivative of an x value, is 0, horizontal tangent line, or if f prime does not exist, could be a cusp, or maybe we've got a vertical asymptote, something like that. Jump discontinuity does not exist. If the derivative doesn't exist, then x equals k is what is known as a critical number, a very important number. Critical numbers are where relative maxes and mins could occur. Just because you have a critical number does not necessarily mean you have a relative max or min, a hill or a valley. More on that in a later lesson. So we're going to be instructed here to just simply find the critical numbers of each function. So again, a critical number is where the derivatives equal 0. It's a possible hill or valley. It's where the derivatives equal 0 or is undefined. So I take a derivative, f prime of x. And that's very simple, right? In this case, it's going to be 3x squared minus 12x. And then I'm going to set it equal to 0. I want to know where the derivative is 0. So I take this and I set it equal to 0. And now I go to algebraic land, right? I factor out a GCF of this thing. So that's going to be 3x times, this will be x times 3x is 3x squared, minus 4 times 3x, negative 12x, equal to 0. Now all we need to do is set each piece equal to 0. So 3x equals to 0, x minus 4 equals to 0. Solve. X is equal to 0, x is equal to 4, adding 4 to both sides. These are your critical numbers. Now, if your teacher ever asks you for a critical point, I'll just do this once. A critical point is simply just plugging these into the original function to find the y value. So you get the point at which the derivative is 0 undefined. So that would be f of 0 to find the y value. Plug in the critical number. 0 cubed is 0, minus 6 times 0 squared still 0. So the critical point would be 0, 0. And in this case, we'd plug in 4. So that'd be f of 4. A little bit more math involved here. 4 cubed is 64. I'm going to do this out a little bit. 4 squared is 16 times 6 is 96. That would equal to negative 32. So the point is 4, negative 32. So these are your critical points, your critical numbers, the x values of 0 and 4. All right, on to this one. Where is the derivative equal to 0 or does not exist? Well, let's take the derivative dy dx is equal to 1/3 x to the negative 2/3. Now be careful. You don't want to set this equal to 0 because you might erroneously say that x equals 0 gives you where the derivative is 0. It's not true. You've got a negative exponent. If you have a negative exponent before you solve it, I think it's worth our while to rewrite this. So it's 1/3 x to the positive 2/3. Now, a couple of things. First, this will not equal to 0. Why not? Because the only way for a fraction equal to 0 is if you have 0 divided by a number that's not 0. 1 will never be 0. The numerator can never be 0, in other words. So this derivative cannot equal 0. However, the denominator could. So 3x to the 2/3 could equal 0. And when it does, that would make this derivative undefined at a certain point. That occurs when x to the 2/3 equals 0, which is when x equals 0. Okay, so what does that mean? Well, that is a location where the derivative does not exist. So f prime dne at x equals 0. Remember, that still makes it a critical number, and we're going to take a look at the graphs of each of these on the next slide to see why these critical numbers make sense. So we had x equals 0 and x equals 4, and then x equals 0. So again, on this function, here was x equals 0. That's a place where the derivative was 0. Here's a place where x equals 4, a place where the other derivative equals 0. Notice we do have a relative maximum and minimum respectively here. Again, just because your derivative is 0 does not guarantee a relative max or min. Think about one thing, a horizontal line. That would have a derivative of 0 everywhere, but there's no hill or valley going on there. Just one example of many where you don't have to have a relative max or min where the derivative is 0. We had a derivative of undefined right here at x equals 0. We don't have a hill or valley there. So in fact, the reason why we've got a derivative that's undefined is because the tangent line is actually vertical at this point. So the derivative does not exist at that point. It was a critical number. It's worth checking for a relative max or min, but we don't have one. And so there are no relative max or mins on this curve because there's no other critical numbers. Very cool. All right, on to just one more. Oh, you know what? No, let's stop there. I'm going to do this one in a different video. How about that? See you in the next video. And this is like a sneak peek of it, like Back to the Future.